back to Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we profile some of the most amazing, jaw-dropping scientific developments that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, let's move on now to the first listener phone call.
Hi, this is Ken. I'd like to ask why haven't they used artificial diamond manufacturing to make more effective weapons, like, for example, diamond armor, or, like, for example, diamond bullets? And also, if they were to use diamond bullets, would the ballistics be different? For example, would the rifling on the barrel have to be changed? Or would there be different kinds of ballistics in response to diamonds because they can conduct heat more effectively? I'm just wondering what the practical applications are because it's been around for about 20 years. Same as the applications, for example, what would happen if you had, like, for example, an aerogel bullet, or like a bullet made of aerogel, or armor made of aerogel. Thank you for your time.
Okay, well, I have a personal interest in armaments because I was in the United States infantry for about 2 years at the height of the Vietnam War. In fact, I had a chance to fire practically every single weapon in the United States military's arsenal, starting with M16 rifle, going all the way up to bazookas, anti-tank weapons, all the way up to scale. Well, first of all, you are right that we can make artificial diamonds. That's right. In fact, gem quality artificial diamonds, and that's why the De Beers and the Oppenheimer people, they are very cautious about this because they know that if we scientists flood the market, it could really send diamond prices plunging, and the whole ceremony around engagement and marriage and stuff like that could be affected. That could affect the multi-billion-dollar jewelry market. Recently, I was reading that the De Beers people, yes, they want to accommodate artificial diamonds. But let's address your question about the military applications. First of all, we think that diamonds are the hardest substance around, but that's actually not true. It turns out that graphene is tougher than diamonds. Graphene is nothing but a single layer of molecular carbon, and it is so strong you can put an elephant, balance it on a pencil, and put the pencil on a sheet of graphene, and the graphene will not break. However, graphene is very hard to create in pure form more than just the size of your fingernail. So it means that coatings, in the future coatings, will use carbon either in diamond form or perhaps more likely in graphene form as a way to shield the bullet from the different kinds of forces that would experience after it's being fired. But do you really gain that much advantage? Well, you said that will we have to change the clicks on a rifle? And probably not. It turns out that the basic physics of projectiles is given by Isaac Newton, and the projectile physics is basically independent of what the bullet is made of in terms of its trajectory, in terms of how many clicks you want to put on the rifle. So even though you would have better armor-piercing capabilities with nanotechnology and coating armaments with nanotechnology like graphene, you're not going to have to necessarily change the settings on a rifle because those settings are pretty much set by Isaac Newton's laws of motion, which in turn, believe it or not, are more or less independent of what the bullet itself is made of. But anyway, some people think that even the bullets of today may become obsolete as they become artificially intelligent. In other words, it may be possible to create a whole new series of armaments using high tech. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, we are taking your listener phone call in this hour. Okay, moving right along now, let's take the next listener phone call.
Yes, this is David in Central Lake, Michigan, calling with station WMKT. My question is about the tunneling electron microscope. Has there been any developments or research into improving upon that? I know we keep talking about these more and more telescopes you can see farther and farther in the past. Is the electron microscope the end-all and be-all, or Has there been any progress on improving upon that? Thank you.
Well, the electron microscope allows you to get these gorgeous, surrealistic, alien-like photographs all the way down to the cellular level. And it gives us a whole insight into a new world, the world of nanotechnology, the world of Mother Nature, the world of how Mother Nature performs its biological feats. But there are limitations given us by the quantum theory, which happens to be my specialty. It turns out that when you get down to molecular distances, the electron beam gets more and more energetic the smaller it gets, which kind of like violates common sense. But if you want to get an electron microscope that's even more powerful than the one today, you have to have a wavelength smaller and smaller and smaller, and that becomes disruptive. In fact, at a certain point you hit X-rays, and X-rays, as you know, can cause cancer. It can knock the crap out of atoms. And so that's the problem with microscopes. We have optical microscopes with a wavelength on the order of several hundred atoms, but when you start to go to ultraviolet radiation and eventually X-ray radiation, the wavelength is about the size of an atom. So in principle, you can actually, quote-unquote, see an atom. And that's what electron tunneling microscopes can do. I played with one. I was filming with BBC television a few years ago. We flew down to San Jose, where at the Bell Laboratories, they had a tunneling microscope where I could actually, quote, touch individual atoms. That's right. They look like ping pong balls. Ping pong balls on a computer screen, and you can actually manipulate them one by one and spell different letters out of individual atoms. This is amazing. Think about that. Spelling out, for example, IBM, atom for atom, each atom the size of a ping pong ball, on a computer screen, and manipulating them by hand with a handheld device. But like I said, once you get to even smaller frequencies, smaller wavelengths, energy increases by Planck's law, and at that point it becomes very disruptive, and basically it blasts these atoms apart. The molecules are sent to smithereens, and your X-ray microscope becomes useless. So there's a trade-off. So electron microscopes are pretty much the limit of what you can do unless we learn how to manipulate X-rays without causing the damaging effect of high-energy particles. Okay, well, let's move right along now to the next listener phone call.
Hi, hello, Dr. Kaku. My name is George Gonzalez, and I'm calling from Corpus Christi, Texas, radio station 1360 AM. My question is about black holes. Black holes consume other stars, other planets, and then they eventually, I guess, explode. Do they eventually take over each other if there's enough black holes in the universe or in a galaxy, and then create another universe or another dimension? Is this the process of the universe being rebuilt? And I'm a big fan of yours. I've bought your books, and if you could explain that, I'd appreciate it, and hopefully I can hear it in this show, because I don't get to hear every show. Thank you. God bless. Thank you.
Okay, well, you asked a question that is at the cutting edge of modern physics, because it has to deal with how the universe itself will die. We think that the universe will have 5 basic stages in its lifespan. The first stage is the Big Bang, and when temperatures are extremely hot, and the universe consisted of a huge, gigantic ball of hot plasma gas. That's the first stage. The second stage of the evolution of the universe is when all this high-energy matter began to condense into atoms and condense into stars, giving us what is called the stellariferous era, the era of stars. And that's the era that we live in. We live in the era when the universe is brilliant and lit up by all these dazzling, shining stars lit up by the process called fusion, which is the burning of hydrogen into helium. But, hey, let's face it, all things must pass. Eventually we go to stage 3, billions and billions of years from now, when the stars begin to twinkle out, we burn up most of the energy and fuel in the stars, and the stars become neutron stars, dead stars, or black holes. That's the third era. The fourth era is when the whole universe becomes nothing but black holes. A very sad era. No more stars generating light. The universe essentially consists of black holes. The universe is completely dark. The night sky is completely dark. And the fifth era is horrible. The fifth era is when the universe itself dies and black holes radiate their energy into outer space in something called Hawking radiation. Hawking radiation means that black holes are not really black. They're gray. They will seep out gentle radiation, which may dominate stage 5, when the entire universe becomes invisible and seeps out this radiation until, as you pointed out, eventually they will explode and there's nothing left but a gas of electrons and neutrinos. Sounds kind of horrible, right? Well, my personal attitude is, first of all, don't worry about it. It's going to take place trillions upon trillions of years from now. And second of all, by then, if we survive, we will have technology trillions of years more powerful than anything we can even imagine today. We may even have the power of a god, in which case we may want to create a lifeboat, an interdimensional lifeboat, and escape the universe. Believe it or not, I'm not the only physicist who's proposed this, but to create an interdimensional lifeboat so that we can leave our universe and go to a neighboring universe in the multiverse, and then we can mess up that universe as well. And believe it or not, yes, there are scientific articles about this. The ultimate doomsday, when the universe dies not in fire, but in ice. Okay, let's move on now to the next listener phone call.
Hey, this is Dave P., 1340 KPRK, Livingston, Montana. And I was wondering what your opinion is on wormholes. Are they feasible to use, or is it just a hoopla? Right.
Well, if you're a fan of Star Trek, you know that wormholes are very convenient ways to zip across the entire galaxy and the universe, basically a shortcut through space and time, and it's not completely ruled out. We physicists believe that at the beginning of time, that is, at the Big Bang, there may have been tiny wormholes that existed with the original singularity that created the universe. As the universe rapidly expanded in terms of what is called inflation, these wormholes may also have been stretched and allow us to then communicate and go back and forth across the universe. Now, if you're a fan of Star Trek, you know that there's a problem there, and that is stability. It turns out that most of the wormholes in Star Trek are unstable, and you can't really use them to go back and forth. However, that leaves open the possibility that some of them are stable, in which case we may actually be able to go backwards and forwards. So what are the pros and cons of this? The pros and cons of this are, well, first of all, we've never seen one. They are theoretically possible, but let's take a short commercial break. And after the break, we'll continue a discussion of wormholes and space and time. With Professor Michio Kaku. In this hour, we are taking your listener phone calls. You are center stage. Well, before the break, we had a question about wormholes. First of all, what is a wormhole? A wormhole is a shortcut through space and time, like the looking glass of Alice. Think of the looking glass of Alice. One side of the looking glass connected Oxford, the countryside of Oxford, to this strange world called Wonderland by going through this looking glass, which is a wormhole. In fact, who was Charles Dodgson? Charles Darwin, otherwise known as Lewis Carroll, was a mathematician, a professional mathematician at Oxford University. He was well acquainted with different kinds of topologies, including multiply connected spaces. That's what mathematicians call them, multiply connected spaces. We physicists simply call them wormholes. And they are gateways to other universes. Stephen Hawking, the late Stephen Hawking, in his latest book, published posthumously, writes that yes, wormholes are probably possible. They seem to obey Einstein's laws. And how stable are they? We don't know, but yeah, they do seem to be valid solutions of Einstein's equations. Einstein himself stumbled on them in 1935. Back in the 1930s, Einstein was puzzled by this nagging question. What happens at the center of his equations, the center of a black hole? His equations predicted everything blows up, becomes infinite, and he was very unhappy about that. In physics, we have no such thing as infinity. But there it was. At the center of a black hole, it looks like a funnel. Everything falls into the funnel, but at the very center of the funnel, gravity becomes infinite. Einstein hated that idea because why should something be infinite in a finite universe? So then he took two funnels, stuck them back to back, mouth to mouth, two funnels, and he came up with a wormhole. So the creator of the wormhole was Einstein himself in 1935 in a paper he published with Rosen. And in fact, today we call them Einstein-Rosen bridges that connect us to distant points in the galaxy. Are they possible? Yes. Do they actually exist? We don't know. Can we create them with our technology? And the answer is no. You need the energy comparable to that of a black hole before you can start to play with wormholes. In other words, this is something for a very advanced civilization, perhaps type 3. We are type 0. Sorry about that. Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. This is the time when you can talk back to the radio or the internet. Okay, let's move right along now to the next listener phone call.
I was wondering about life on other planets. My name is Diana Taylor. My call letters are KTEC 89.5 from Klamath Falls, Oregon. My question is are there going to be other races on planets, and are any of the races going to be excluded because they had a skin color change? Thank you for answering that question. I'll listen on the air. Thank you.
Well, first of all, I agree with most of my colleagues who are also scientists that they're probably out there that, why should we be the only game in town? We think that, for example, microbial life may be actually quite common throughout the galaxy. We've already located 4,000 planets circling other planets. The census is that there could be up to several billion Earth-sized planets in our own backyard, the Milky Way galaxy. Now, are they going to... Will they have different skin color? Well, probably they'll look totally different from us. For example, take a look at a lobster. A lobster is familiar. They exist here on the planet Earth. But imagine a race of intelligent lobsters that evolved over millions of years in a different planetary system. They're going to think different than us. They're going to act different. They will have different goals, different dreams, different ideas, and they could also be intelligent. And remember, lobsters are on the Earth, made out of the same DNA that we are in outer space. We could have a totally different kind of architecture than what we find here on the planet Earth. Now, what we have on the planet Earth is, first of all, carbon chemistry. Carbon has 4 bonds, meaning that you can create all sorts of molecules like DNA in water. So we do think that chances are, if intelligent life exists someplace in the galaxy, they'll arise from the oceans, and they'll probably be carbon-based, though, of course, we're not totally sure of that. And how did we become intelligent? Well, probably three things. We're not sure, but three things propelled us to become intelligent, we think. First is stereo eyes, the eyes of a hunter, not the eyes that face to the side of our face, as in a deer or a mouse. Those animals that have eyes to the side of their face are prey. However, animals that have eyes to the front of their face, like wolves, lions, tigers, foxes, they're predators because they use stereo vision to lock on to the prey. And predators are smarter than prey. So we think that they could be descended from predators. Second of all, we have an opposable thumb. Other animals may have claws, tentacles that are perhaps just as dexterous as our opposable thumb, but some kind of grasping instrument is necessary. And third, language. Language allows you to communicate information from generation to generation. But have you ever seen Mama Bear talk to Baby Bear, instructing Baby Bear to watch out for human hunters? No. Animals largely operate by instinct, while we humans rely upon instinct and also knowledge handed down from generation to generation. Now, let me ask you a question. How many animals on the earth have all three? Many animals seem to be kind of smart, but they have claws, they don't have fingers, they don't have manual dexterity. The octopus has tentacles, but its eyesight is rather poor, has no language that we know of. And so we realize that only humans on the planet Earth have all three ingredients perfected pretty efficiently to create Homo sapiens. Now, where does skin color come into this? Well, it doesn't come in at all, because in outer space, who knows? Who knows what they're going to look like, but probably, though we're not certain, they will have some combination of the three technologies that I mentioned. Hand-eye coordination with maybe stereo eyes and language. Welcome back to Science Fantastic with Professor Michio Kaku. Yes, once again on Science Fantastic, we are taking your listener phone calls. Okay, now let's move on to the next listener phone call.
My name is Wayne Giuliano. I'm calling from Eldon, Missouri, and my question is about the existence of nothing. Is it possible for nothing to exist? Presently, atoms, light, space, time exist. Could there ever be a place where nothing exists? Thank you.
Well, you ask a rather embarrassing question, because common sense says yes. Common sense says that between atoms there is nothing. And we even demonstrate that to our beginning students by getting a piece of uranium, putting it behind the person's back, and then putting a Geiger counter in front of their stomach. And the radiation goes right through your body, energizing the Geiger counter as if you are not there at all. And we use that to demonstrate the fact that you are basically made out of nothing. However, once you get to the quantum theory, then you realize that there's always uncertainty in everything. Even nothing violates uncertainty. So that means that, for example, black holes cannot be totally black. They must be gray because of the uncertainty principle. Black is certain. Gray is not. And the uncertainty principle says there's uncertainty in everything, including blackness. And that's why black holes are gray and not black. And black holes must gently seep out radiation called Hawking radiation. Same thing for nothingness. That between atoms there is something. And what is between atoms are virtual particles. Particles that dart in and out of the vacuum. They emerge from the vacuum and then go back into the vacuum. These are called virtual particles. They only exist very briefly for a fraction of a second. And for the most part, We can ignore them, but you have to put them in when you do a quantum mechanical calculation. Now, why should we care about this? Because this means that nothingness is actually frothing with activity, with virtual particles dancing in and out of the vacuum. And some of us believe that that's where the universe came from. Because not only can you have virtual particles dance in and out of the vacuum, you can also have virtual universes as well. Now, most of these universes pop into existence and then pop back into the vacuum, never to be seen again. However, because of quantum mechanics, there's always a certain probability that one of these bubbles will pop out of existence and just keep on going. That could be the Big Bang. Now, some people who are religious like this idea because even the Bible seems to hint at the fact that the universe came out of nothing, out of nothingness, and everything you see around you is a product of nothing. Now, this quantum mechanical uncertainty also applies to black holes. Everyone knows that black holes are black. They suck up everything. But you see, blackness is a perfect color. And in quantum mechanics, you cannot always have perfection. You always have uncertainty with regards to radiation, mass, and velocity, which means that black holes must be gray. They must gently seep out radiation. And that means that pure nothingness can also not exist. Quantum mechanics says that even nothingness must have uncertainty. And sure enough, when we make very delicate measurements of a pure vacuum, we find out that there's energy there called zero-point energy. It's very small, but there it is, undeniable. And this energy is created because atoms and anti-atoms can jump out of the vacuum, disintegrate, and go back into the vacuum. So the vacuum is frothing with activity. Particles jump out of the vacuum, disintegrate, and go back into the vacuum. And so there's constant agitation within nothing, which is measurable. It's undeniable. Violates everything that you know about common sense. But hey, what does the universe care about your common sense? Now, why should you care about this? Because some people think that explains the origin of the universe. You see, not just particles can jump out of the vacuum, but entire universes can also jump out of the vacuum. Universes pop into existence with a big bang, and then pop back into nothingness with a big crunch, almost immediately after. Now, some people think that our universe was the exception, because there's a certain probability that some of these universes will just keep on going. So our universe may have popped out of nothing and just kept on going to create the Big Bang. In other words, out of nothing came everything. Now you may say to yourself, come on, what about particles, energy, matter? That's not zero. Well, it is. Because what is the net charge of the universe? Electrons have negative charge. Protons have positive charge, and they balance out. The total net charge of the universe is zero. But what about spin? Well, galaxies spin in different directions. You add it all up, and what do you get? Zero. Well, what about matter? Matter is not zero. Well, if you add up the total amount of matter we can see with our telescopes, add to it the negative energy coming from gravity, because gravity has negative energy, what do you get? Zero. A universe out of nothing. Okay, well that's it for Science Fantastic.